Okay, this is now lecture 4 of my part of the spectroscopy course, and we're going to be looking at nuclear magnetic resonance spectroscopy. There are some additional notes on my place, some extra PowerPoint slides, which you might find useful just to have a look through to get a bit more background knowledge about why we do this analytical technique, why it's useful, and just to be able to back up some of the things which I'll be talking about during the lecture course. So what is nuclear magnetic resonance? Well, many atomic nuclei possess a property called spin. So that really means that nuclei behave a little bit like bar magnets. So when there's no magnetic field, the nuclei are aligned in lots of different directions, but upon applying a magnetic field, the spins will line up either parallel or anti-parallel to the magnetic field, which I've just indicated with an arrow up the side here. So if the spins are parallel to the magnetic field, that's a low energy state. If they are anti-parallel to the magnetic field, that's a high energy state. So once they're in this state, we can then apply a radio frequency pulse. And that radio frequency pulse can make the spins go into a high energy state. We're applying energy. So the spins which are in a low energy state will then go into a high energy state and align anti-parallel to the magnetic field. Once we switch off that radio frequency pulse, the spins will return to a low energy spin state and emit radio frequency energy. And this is what's called relaxation. And the frequency that's emitted when the nuclei relax to go back to a low energy state depends on the nucleus involved. So how and when are we going to use this type of spectroscopy? Well, you use it an awful lot in lab sessions in second and third year to confirm the identity of the things that you're making. You'll use it during research projects, so that could be during a placement or during your fifth year or your final year, and also in the exam and class test. You'll be needing to apply these skills. So let's talk a little bit more about these basic principles. How do we know if something has spin? Well, atomic nuclei with either an odd mass, an odd atomic number, or both have spin. And we can define spin by a spin quantum number, which is termed as I. And the number of allowed spin states which a nucleus has can be calculated by multiplying the spin quantum number by 2 and adding 1 to it. And just to recap what I said on the previous page, the spin states of a nucleus are of equivalent energy until we apply a magnetic field. So when we apply this magnetic field and then we apply a radio frequency pulse, and we then switch the pulse off and a radio frequency is emitted, this is called a resonance frequency. So it's a frequency that's emitted upon relaxation, and that frequency depends on a few things. The first is the identity of the nucleus. So is it a proton? Is it a carbon-13? Is it fluorine-19? But it also depends on the environment of the nucleus. So is that carbon part of a CH3 group, or is the hydrogen part of a CH3 group? Is the hydrogen part of an hydroxyl group? Is it an sp3 carbon or an sp2 carbon? And this all causes a difference in the chemical shift. And the chemical shift is the data that we get out from running an NMR spectrum. So we need to establish which nuclei have spin. Not all nuclei do have spin. So nuclei which are what we call NMR sensitive include deuterium, and that has a spin quantum number of 1. We have a number of nuclei with spin quantum number of half. So phosphorus 31, fluorine 19, nitrogen 15, and hydrogen as in a proton. So carbon 13 has a spin of a half, but carbon-12 doesn't. So we're going to be looking at carbon-13 NMR during this course, and carbon-13 is an isotope of carbon. It's not very abundant, 1.1%, but there's enough of it in order to be able to analyse molecules by looking at the different carbon-13 environments, and we use that an awful lot in research in order to work out the structure of molecules. So just to note that I've said that carbon-13 has a spin of a half, carbon-12 has a spin of 0, so we can't analyse carbon-12 by NMR. So let's now look at carbon-13 spectroscopy. So naturally occurring carbonaceous materials contain mostly carbon-12 and a little bit of carbon-13. And all chemicals which are produced from these sources will also contain this similar ratio of carbon-13 to carbon-12. So for instance, in methanol, we have methanol with carbon-12. It's about 98.9% of a sample, and then 1.1% of that sample will have carbon-13 within it. So given the carbon-13 nucleus has a spin of a half, it's sensitive to NMR, and we can detect low concentrations of this carbon-13 based methanol. So because of this low abundance of carbon-13, it's unlikely that molecules of medium molecular weight will contain more than one carbon-13 atom per molecule. So if we look at this molecule here, it's propanone or acetone. 98% of that will be have the 3 carbons as carbon-12, and the final 1.1% is likely to have a carbon-13 as the CH3 and a carbon-13 as the carbonyl carbon. And we call these different states, if you like, isotopomers, where we've got a different carbon atom as a carbon-13 in each molecule. So only the molecules with carbon-13 in them are going to be observable by carbon-13 NMR. We can't see carbon-12 in NMR spectroscopy. So the spectrum that we see is therefore a composite of the spectra of all the isotopomers. So the composite of the spectrum of this one, which will pick up this carbon here, and this one, which will pick up this carbon here. And so we see 2 carbon environments. So another way of looking at this is to look at a molecule and looking at whether it has lines of symmetry and what carbons are potentially equivalent in the molecule. And we mean equivalent as being in the same environment. So the number of lines in a carbon-13 spectrum corresponds to the number of different carbon atoms in a molecule. So that isn't just counting the number of carbon atoms, but we need to look at the type of carbon. So if we see this molecule called, it's acetone, propanone, it looks like this, and we've got a line of symmetry down the middle here. So these 2 red carbons are in exactly the same environment because we can flip the molecule over and the molecule looks exactly the same. And so we've just got this central carbonyl carbon here, and then this CH3 environment, which is the same as this one. And that's why we only see 2 peaks in our carbon NMR spectrum. Okay, so how do we apply this concept of isotopomers and the number of peaks that a molecule gives in a spectrum to actually a spectrum itself? So when I talked about radio frequency pulse being switched off and the spin of a nucleus returning to its low energy spin state and emitting radio frequencies, this frequency is translated to a dimensionless scale which we call chemical shift, and that's the x-axis of our NMR spectrum. So generally we have to reference our peaks to something in order to be able to correctly apply a chemical shift to different resonance frequencies, and normally that reference is tetramethylsilane. We give that a shift which we call delta. Delta is the shift of about exactly 0 ppm, and we can use that as a reference, or the alternative is to use our residual solvent, so the thing which we're actually dissolving our sample in, as the reference. And our residual solvent could be something that's it's usually something that's deuterated, so deuterated chloroform or deuterated methanol. And these are normally deuterated because we also use them for proton NMR spectroscopy, and we need to minimize the number of actual protons in our solution in order to get a good spectrum. So the chemical shift of a peak is dependent on the chemical environment of the nuclei. So I spoke a bit about, is the carbon part of a methyl group, or is it part of a carbonyl group or an alkene? And we always quote the chemical shift as delta. So that's along our x-axis. And our y-axis is the signal intensity, and we're going to look at a few examples of NMR spectra shortly. So this box here is really the key part of the course that you need to learn. It's got a chemical shift range along the bottom, and you see that it's a bit different to other graphs that we normally deal with, where 0 is on the right hand side and then parts per million increases towards the left. So let's go through this logically. So if we get peaks between 0 and 40 ppm, they're generally indicative of aliphatic carbons in a molecule. So we have carbons linked by single bonds. If we see a higher shift, that generally tells us that we've got aliphatic carbons next to a heteroatom. So by that I mean a carbon bonded to either oxygen or nitrogen or chlorine or bromine, a carbon that's not bonded to another carbon or a hydrogen. As we go up the scale between 100 and 160, we have unsaturated carbon atoms, so corresponding to alkenes and aromatic molecules. And this area here really is key, between about 160 and 220 ppm, where we see carbonyl carbons, and the shift of those peaks depends on whether we have acids or esters, and they're between 165 and 185, give or take a few ppm, or ketones or aldehydes, which are a lot higher shift, between 190 and 220 ppm. So let's now look at a few examples of spectrum. We're going to start with something really simple, methanol. So our carbon spectra generally tend to be proton decoupled, and by that we mean that we simplify the peaks because carbon-13 can interact with protons, with hydrogen atoms in the molecule, and form a much more complex spectrum. But we manipulate the data so the peaks are a lot simpler. So in methanol we just have one carbon atom, so we can expect to see one peak, and it sits about 50 ppm. And that's because it's an aliphatic carbon, but it's also bonded to a heteroatom. It's bonded to this oxygen as part of the OH group. This peak here is just our solvent. We've dissolved a bit of methanol in chloroform that's deuterated, and it gives this peak here. So we can ignore that peak when we're looking at the spectrum and just focus on the other peak that we see. So what about going back to our initial example of acetone, where we have two carbon environments in the molecule. Because we've got a line of symmetry down the middle, both methyl groups are what we call equivalent. So we're seeing two peaks. We've got our solvent peak about 77 ppm, so we can ignore that. And we've got one peak down at this end, about 30 ppm, and that's because it's a CH3 group and it's not next to a heteroatom. This carbon is bonded to another carbon. It's not bonded to an oxygen or a nitrogen or another heteroatom. The other peak we see is up here, about 206 ppm, which is characteristic of a ketone carbonyl carbon. So the carbon that's double bonded to the oxygen gives a peak about just over 200 ppm. Let's now look at another aliphatic compound, and it's ethanol. So we've got two carbon environments in this molecule, a CH3 bonded to a CH2. So that peak is going to appear between 0 and 40 ppm, so right in the middle here. And we've then got a CH2 that's not only bonded to a CH3, but it's also bonded to an OH on the other side. So this carbon's bonded to a heteroatom, so we see that peak at a higher shift, just below 60 ppm. And again, we've got a solvent peak, which we can ignore. So that ties up lecture 4, and we'll start the next lecture, which will wrap up the course by looking at some more examples of carbon NMR spectra.